Hello, good evening. Name is Boris Jeremic, professor at UC Davis. With me are Dr. Han Young
Hello.
and Mr. Heshenwang.
Hi.
And we're going through demos of how to run real easy, simple examples. I'm going to share my screen now. And I'm going to show you the example. Can you see this example?
Yes.
Yeah.
This is on page 40. This is again from set of examples that are prepared for a 3-day short course. You can download those directly from Real Easy Info, or they're also available within these lecture notes. Let's go back to page 40. This is an example that actually has solids and beams and shells and contacts, but I'll let actually Dr. Yang talk about this example. So Han, please take over, share your screen.
Okay. Yep. Okay. Let me just share my screen. And here we go.
Good. Yeah.
Okay. Can you see my screen?
Yeah, we can see your screen. Excellent.
Okay. Yeah. So as Professor Boris just mentioned, so here is our model. So in this model, basically we are showing you all like the majority of the element types that we're going to use in a simulation like this. So we have beam elements right here. We have some shell elements on the other side, and then we have a number of solid brick elements at the bottom. And then to simulate the interaction between the structural element and the solid element, we also put these contact interface elements between the structural elements and the solid elements. And you see they are represented by this small red spheres here, because theoretically they're supposed to be zero volume elements, but in order to visualize them, you have to represent them somehow. And this is the way we chose to represent them, to kind of show them that they're there. So this picture just gives you an idea of what kind of example we are building here. So next, I think
just tell them the boundary conditions. Bottom is fixed, right?
Oh yes, that's right. So the only constraint, the only boundary condition for this model is all the bottom nodes for the solid are fixed, and then later we're going to apply some load, and then we're going to let it to free vibrate, and we're going to see how the system responds. Okay. Yeah, so I think next we are going to move on to the input files.
Yes, show them what do you have for input files. Yes, show them first of all what are all the files that you have in the directory.
Okay, so here is the directory I have right here. As you can see, this is the picture I just showed you, but other than this picture, all these files are the input files we are going to use. This main file right here is the, well, it's named as main file, is the main input file here. And later when I go through the main file, you will see that it actually calls all the other supporting files that's going to be part of the input of the simulation.
So main file is the main file, and all the other files are just organization. This is just a nice way to organize things in a smaller files, so they're easier to manipulate. And you'll see, Han is going to show you that we can actually include those outside files. It just helps organization of the system. Yes, go ahead, please.
Yes. So here is the main file. So at the beginning, we always have the model name. So in this example, because we have all the element types, so we have solid, beam, shell interface, so we just call it that way. So this is the model name. Then next, we move on to definition of the materials. So here, first, we have the definition for material definition for solid elements. This is material number 1. We have mass density, elastic modulus, and Poisson ratio. Note that this is a linear elastic kind of material, so there won't be any damage or energy dissipation happening in the solid elements. Similarly, we have the material definition for shell elements. You see that this is a different material, so it's use another number to name it. So material number 2, it is also a linear elastic material. So we have a slightly different material properties. We have a different density. We have a different modulus, but the format is the same for the two materials.
And then, please note that this you need units. This is you need units. So yes, you know, mass density unit is kilogram per meter cubed. Elastic modulus is gigapascals. In this case, you can use megapascals, pascals. a full list of units is given in real easy manuals and in lecture notes. Yes, go ahead. I'm sorry.
Yes, yeah, it's okay. So, okay, so now the next one is defined. We define the material properties for the contact or the interface elements. So, basically, those material properties will define how the interface element will behave in the axial or the tangential direction. So again, all the definition of this material parameters can be found in our online manual for real easy or in lecture notes. So you can go ahead and see the exact definition of those material properties. Okay, so after we define the material, so next we move on to define the geometry of the model. So first we have the nodes. They are included in this supporting file, this node.fei file. So let's just go ahead and open that. So as you can see in here in this node file, we are defining all the nodes that's going to be used for this model. So we're gonna have basically two types of nodes in this model because we are actually because we have different type of elements. So the first are the group of nodes that's gonna be used for the solid elements, and each of those nodes are gonna have 3 degrees of freedoms. So as you can see, there's a number of those nodes that's gonna be all the way down to I think about a little bit more than 600 of those nodes. Those are the nodes for the solid elements. And then next we define the nodes for the beam elements and the shell elements. The difference between those is a different number of degree of freedom is used here. So now for the beams and shells, there's going to be 6 degree of freedoms, as you can see here. Okay. So those are the nodes definitions. And then after we define the nodes, we can build the elements. So the next file we're going to show is the element.fei file. So this is the definition for the elements. Let's go to the top. So again, we have basically 4 types of elements. The first one is the solid bricks. So we are using 8-node brick. This is the element type. Again, you can find the definition of all these element types in our online menu for real easy. So first we define a number of solid bricks. I think we have about 100 of those. Oh, sorry, we have 400 of brick elements right there. And we can see for those brick elements, we are using this, so it's an 8-node brick, so we will have 8 nodes associated with the element each. And then we are using the material number 1, which is we already defined earlier here. This is the material number 1 we use for solid elements. Okay, and then next we have the shell elements. So again, similarly, you would have an element number, you have an element type. So again, you can find the exact definition of this shell element in our online menus. And then similarly, we have the beam elements. We also have the contact interface elements between the beam shells and the solid. So this is the file for all the elements. Now we go back to the main file. So we continue to the main file. The next one is the boundary conditions. So let's open the boundary condition file. So as we mentioned earlier, the only boundary condition we have here are to just basically fix the bottom of this model. So we're fixing all the degrees of freedoms for the nodes at the bottom of the solid here. So this is what we are doing. So we fix all of them. Those are those nodes. So that's the boundary condition file. Okay, so now we have already defined the geometry and the boundary condition of our model. So before we apply any load, it's always beneficial, it's always useful to have this step called check model. So once you run this command called check model, the simulation will basically check if all the connectivity or the definition of your model is correct. And if not, it will tell you where is the problem. If it is correct, it will tell you it's okay. So Professor, should we?
Han,
Yeah.
if I may, so check model is also going to create output files for visualization. So you do not have
Yes.
to run
So.
anything. You essentially
Yep.
just visualize model without without any results.
Yes. Should we run this check model first?
No, let's just talk about the whole thing, then we'll show just
Okay.
like last time. Yeah, I mean it's a good idea to
Okay.
run check model without any simulate steps below, but at the moment we'll just run how many loading stages you have? We have 3 stages: check model plus load plus 3 variations. So we're just going to run all 3 of them, but we're going to show the output that's going to actually have a check model phase, which is going to be no results, just the model how it looks like when it's defined.
Yes, yes. Okay. So after the check model, then we have our 2 loading stages. So the first one is basically a simple nodal loads on the beam and the shell. So we call this loading stage just load. And all the loads are defined in this another file right here. So let's just go ahead and open this. So this is the load file. So we are gonna have, let me open this picture again. So we are gonna put some nodal loads on top of the beam here and on top of the shell element here. So as you can see, there's 1 node on the top of the beam, 3 nodes on the top of this shell part here. That's why we have basically 4 loads. So load number 1 and 2, 3, 4 for the shell. And all of those loads are in the direction, in the x direction. So that's why it says fx. And the magnitude of those loads are defined as this P. As you can see, P, now here we put it to be 3,000 kilonewton. So this is our first loading stage, the nodal loads. And to simulate this load, we need to define basically a convergence test. The reason we are using basically like the iterative solving scheme is because we have the contact interface element, and whenever you have those elements, your model essentially becomes a nonlinear system. That's why you need to use iterative kind of solving scheme, and also you need to define a convergence test. Here we define the convergence test. We check the unbalanced force in the system. Our tolerance here is 100. Basically, it's summing up all the unbalanced force and check if the total unbalanced force in your system does not exceed your tolerance. So basically, we can move on to the next step.
So
And
if I may add, it's a nonlinear system because of those interface elements, and you're going to use Newton to solve that. And what you're requiring the system is to go back to equilibrium within some tolerance, and then you define the tolerance. Excellent. Go ahead. Yes.
yes, and then we say, okay, for each step, you have a maximum number of iteration to be 20. If the simulation goes more than 20 steps and still doesn't converge, that means your system probably has some problem. Instead of just going endless of iteration, you should go back and check your model. So again, yeah, we are using the Newton algorithm, and we are using UMF pack solver. This is the solver we use to solve the global equations. So again, you can find the detailed definition of and explanations of those options in our online menu. So the last thing we need to define is the load factor and the number of steps we are using. So because this is just a nodal load, we are not simulating any dynamic effect in this stage. So we are using static algorithm and simulate 10 steps in this stage. So that's our first loading stage. And the second loading stage basically is a free vibration stage. So what we want to do in the second stage is we want to remove those loads that's applied to the model and let the model to freely vibrate and see the dynamic effect that's happening inside this model. So first we remove those loads. So again, we are putting those commands in another file called remove load. This is how it looks like. So remember, we have basically 3 nodal loads, so we are removing all of them. So that's, you see, just remove load number 1, 2, 3, and 4. So remove all of them. So after we remove all of them, again, we're gonna simulate that. So we again need to define all the simulation options, the convergence test, the algorithm, the solver. So all of these are the same as in the previous stage, but here's the difference. So because as I mentioned, we are trying to simulate the dynamic effect in this loading stage. So we're going to use a dynamic integrator. Here, the one we are going to use is the Newmark integrator. So we are using the options gamma equal to 0.5 and beta equal to 0.25. This means that we are not adding any artificial damping or numerical damping into the system. So theoretically, the vibration should go on forever. Again, you can always adding some damping or the choice of those parameters you can again find in our menu. So here we are simulating 100 steps using the transient algorithm. So the transient algorithm is always used when you're trying to simulate a dynamic process. The size of the time step, we are using 0.001 second. So basically the whole thing lasts in total 0.1 second. Now, that seems like a short amount of time, but because our system is pretty stiff, that means that our vibration is going to happen pretty fast. So in 0.1 seconds later, after the simulation is finished, you will be able to see that it actually already run a number of vibration cycles. So just in this example, just to demonstrate you how the system works, and you can always increase the number, you can always play with the time step just to see the influence of all those things happening to your simulation. And
Okay,
once we are done,
yeah, go ahead.
so I just last thing. So once we are done, we're gonna add this by command at the end of our input file. This is to end the simulation, to properly save all the files, close all the files, and then exit the program. So
Okay, great.
that's all for the input file.
Good, great. So let's run it. Let's go and run the system.
Okay.
Go back to terminal window.
Yep. So this is the terminal window. So I'm just gonna run first. I think
make it a little bigger.
show
Make it
the
a little
program.
bigger so we can see. Make it
Okay.
window a little bigger. I mean, fonts. Well, not that, but I mean the actual size of the window.
Okay.
Yeah. Okay, that's good. Yes, that's perfect.
Right. So first, maybe I should show just the program.
No, well, we've seen. Okay, yeah, sure. Yeah. So
Yeah,
he renamed it sequential and parallel, right?
Yeah.
Yeah, same thing. You see here the definitions, the title and everything. This one was really easy. This is actually Han's branch. It's very close to global release branch. It was built by Han. User is Han. This was actually today, 17th, just a few hours ago. Actually, no, this is. Oh no, I'm sorry. This is current time. Yeah, go ahead.
I think that's that's a small problem with my machine right there, because right now the machine consider all the time to be February 26th. I actually just compiled this one today, but the machine, if I open anything here, I mean it's on the system level, everything is in February. For some reason, I guess because of the coronavirus, the system does not want to go past that date.
Okay, that's fine. So we've talked about these. These are just compatibility versions for preprocessor and post-processor, and okay. So now just quit. Just go out by exit or Zhejian or whichever language you want to use.
To exit the program, we can say there's a number of commands. So let's say we say Zaijian, which is a Chinese for bye.
Okay. Columns.
I'm sorry. I mean, I forgot. I think I should probably say just say bye. Yeah. By saying bye, it says that okay. Have a nice day.
Okay. So let's try to run our program on the main file.
Okay.
Just run it, and then we'll look at the output, and then we'll stop this recording and continue next time with post processing.
Okay. So to run the input file, we just say easy sequential -f, and then the name of the file, main file, and enter. So now the program is running, so it's reading all the elements, because this one has quite a number of elements, so it took a few seconds to do that. So now it's running all the stages of the simulation. So I think now, it's running the third one. As you can see, there are some iterations going on. This is because of the existence of the contact interface element. So the system is essentially nonlinear, so it needs to take a few iterations to run. So now the simulation is finished.
Show them
you
what's
go
inside
out.
the directory. Show them what the resulting
Yeah.
files inside this directory.
Right. Okay. So now we can see this is the directory right now. So other than the input files, we can see there are a number of output files. So this one is the output files associated with the check model stage, which you can see here in the name. And then this is the first loading stage. We named it load. So this is the output file for that loading stage. And then this is the third output file for the free vibration stage. And also we have the logs to record all the output message while running the program. So essentially, these are the files you have once you run the simulation.
And one thing to note is that these files tend to be large because we do save everything. You do not have to decide beforehand which output to save. We save everything, every single element, every single node, everything that's inside element, everything that's inside node. So you don't have to worry about it. You just open visualization tool and you can visualize them all. Okay,
yes, that's correct. Yep.
So we're done with simulation. So we're gonna stop here. We'll be back with the post-processing of this output in ParaView, and Han is gonna help us with that again too. So
Okay.
thank you very much, Han. We'll be back shortly. Thank you. So if you stop, well, I guess I'll just stop the meeting and then
Yeah.
we'll be back in a few minutes. Thank you. Bye. Thanks.
Bye.
Actually, no, I don't want to stop meeting. I just want